In this short video, I want to have a look at a common application of rectifiers, and that is to peak detector circuits. The job of a peak detector is to store a voltage representing the maximum value of an input signal. They're commonly used in applications like audio mixing, where you may want an LED to come on if the input signal ever goes above a certain threshold. Consider this circuit. We have a half-wave rectifier here, formed by a superdiode configuration, which is feeding into a storage capacitor there, the 10 nanofarad storage capacitor. So if the input goes positive, the output of this rectifier here will go positive, and the capacitor will charge up almost to the level of the input signal. However, if the input signal then decays slightly from that maximum value, the output of the rectifier doesn't follow it anymore, because the voltage at this point here is maintained close to its maximum level by the charge stored on this capacitor. And that keeps the inverting input at quite a high voltage. So if the input drops from that maximum value, the non-inverting input will now be below the inverting input, which is close to the value stored on the capacitor. Net result, the output of the op-amp goes into negative saturation. No current flows through the diode, no current can flow into the inputs of the op-amp itself, so the charge on the capacitor then leaks out very slowly through this 100 kilo ohm resistor. And you do want that charge to leak out slowly. What you don't want in an application like an audio level detector is for a loud sound to cause an LED to come on, and then for that LED to remain on forever. You just want it to remain on for long enough for the mixing engineer to notice and then do something about it. And that's what the 100K resistor is for. It slowly allows this maximum value to discharge through that resistor so that the capacitor is ready to be charged up again if the input ever gets to another high level later on. These circuits are characterized in terms of their rise time and their fall time. Now, the rise time is the amount of time that it takes the capacitor to charge up. So that's determined by the time constant of this 1K resistor and the 10 nanofarads of the capacitor. The fall time, or the release time, is the amount of time that it takes that maximum value to decay slowly after the peak signal has come in. And that is determined by the time constant of the capacitor with this 100K resistor here, which is the discharge path for the charge on that capacitor. It might make more sense if we see it working. Here I've wired up a simulation of this peak detector with a 10 ohm resistor here as my charging resistor and a 10K resistor as my discharging resistor. And the input is a pulse signal. So it's going to go high for a small amount of time and then come low again. And this is what happens when you run it. Okay, well, we can see that the capacitor is charging up really quite quickly. Only takes a few nanoseconds to charge up through the 10 ohm resistor and the 10 nanofarad capacitor. But you might notice that this charging characteristic is not the typical kind of charging characteristic that we associate with charging a capacitor through a resistor. Before, when we've charged capacitors through resistors, we've seen the output voltage of the capacitor sort of follow this type of exponential charging curve. And here it isn't. It's going up in a straight line. Why? Well, it's because what you're looking at there is really just the very first part of a charging characteristic like that. What happens as soon as the input here goes above 0 volts right at the beginning of the simulation is that we have 1 volt on the non-inverting input but 0 volts on the inverting input. So the capacitor goes into positive saturation, and the voltage at this point here in the circuit at the output of the op-amp shoots up to plus 12 volts. One diode dropped through a forward bias diode takes you down to about 11.3 volts. And then you've got 11.3 volts across this resistor here, charging up this capacitor, which is at 0 volts right at the beginning of the simulation. So the current flowing through that resistor there is 11.3 volts divided by 10 ohms. That's the initial current used to charge up the capacitor. And the capacitor finishes charging when the charge on the capacitor gets to not 11.3 volts, but to 1 volt. As soon as it gets to 1 volt, the op-amp has both of its inputs at the same voltage and its output will go to approximately 0. At that point here, the capacitor has charged up to 1 volt. And we've still got 10.3 volts across this resistor. So right at the beginning of the charging characteristic, the current is 11.3 volts divided by 10 ohms in this case, and at the end of the charging, it's 10.3 volts over 10 ohms. There's not that much difference in the current, which is why the charging characteristic looks like the capacitor is being charged up by a constant current source. It's not quite constant, but it's very close. The discharge characteristic, however, is much more as we would expect. I'll just run this on a bit. It's the standard exponential discharge characteristic that is typical of a capacitor discharging through a resistor. In this case, the 10K resistor there. This is just a half-wave rectifier followed by a peak detector. You can, of course, use a full-wave rectifier followed by a peak detector, and in that case, your circuit would store the maximum deviation from 0 of your input signal, irrespective of whether that was a positive deviation or a negative deviation. That's all I wanted to say about peak detectors. In the last of these videos, we'll have a look at some more interesting circuits.